Alright, welcome everyone to today's set of lectures. Right? When we started on topic 1 in the class, talking about ideal gases. First here we're going to just talk about the states of gases, okay? And mainly things like pressure, temperature, and other such. Okay. So in this class, right, we're going to be talking about thermodynamics. This is a time invariant quantity, right? Time invariant thing that we're talking about, so time independent, okay? When we talk about time dependence, we'll talk about kinetics in next semester, okay? So this semester we're not talking about time dependence at all. It's time independent processes and quantities that we'll be referring to. Okay. So when we talk about gases, right, what is a gas? What's an ideal gas, right? And what are the state variables of a gas and such, right? So what is a gas, right? Well, it's a phase of matter, right? In this phase of matter, the molecules occupy the given space that it's able to, right? It easily diffuses and flows through things, right? An ideal gas is a gas that has no intermolecular interactions between each other or the walls, right? And have no mass, right? No net size, right? So an ideal gas is essentially an infinitesimally small particle that has no interactions with anything else besides just pure bouncing off things, right? Billiard balls hitting each other on a pool table, okay? Right? Remember from our ideal gas law, right? The variables that describe a gas are things like pressure, temperature, number of moles, and volume, okay? Right? And the equation of state for an ideal gas, of course, is our PV equals nRT. Okay. So as part of that, right, we have pressure, right? As a reminder, pressure is a force per unit area. It has units of pascals, right, which is newtons per meter squared. Okay. You can also use things like bars, or kilopascals, or atmospheres, or torr. Right. There are a lot of units for pressure, okay? PSI, right? And you know, we're gonna at times have to convert between some of these things. You don't have to memorize conversions. You'll just look them up in a table, or if you're doing homework, look them up on the book or internet or something, right? But just keep in mind, right, there are a bunch of different units for pressure, right? And which you want to use an equation kind of depends on what everything else is given, okay? Right, so when we talk about pressure, a very key aspect we should talk about is what is called mechanical equilibrium. Okay, talked about chemical equilibrium before in chemistry, right? Here we're talking about mechanical equilibrium, right? And mechanical equilibrium is when you have two different containers, if you will, two things that are separated by either a permeable membrane or a removable wall or something like that, right? A piston and a cylinder, right? And the system reaches mechanical equilibrium when the pressure between both sides equal. Okay, so mechanical equilibrium, right, is reached in part B here, right, when you have both pressures, right, and the pressure, right, or molecules will flow, or your piston will move from high to low pressure systems to reach that equilibrium, right. So if we have a movable wall here, right, this wall is going to move somewhere to the right in this top figure and somewhere to the left in the bottom figure in order to try to equilibrate the pressure, right? So as it moves to the left, it raises the pressure on the left side and reduces the pressure on the right, okay? And systems want to be at mechanical equilibrium, right? That is where things would like to be. If you let stuff relax and do their thing, you will reach mechanical equilibrium. Okay. This is a very important thing in thermodynamics. We'll talk about it often in this course. Okay. And one of the things that we'll note when we talk about work and reversible and irreversible processes and things like that is that changing your system while it's under mechanical equilibrium versus changing it while it is not under mechanical equilibrium will be giving you two different things. Okay. Will require a different amount of work and require a lot of different things to have those processes occur, right? whether or not you're at mechanical equilibrium. All right, so example here, right, for pressure, right, if I want to get the pressure of some 65 kilogram person, right, on ice skates, where the contact area of those skates on the surface of the ice is around 2 centimeters squared, right, we'd ask how much pressure is exerted on that ice, okay, right, and if we recall our pressure, right, pressure is force over an area. We're already given the area of 2 centimeters squared, right? And we want to convert that to meters squared. So we're going to have to do that conversion, right? And the question is the force, what is it? Well, the force is just gravitational force, right? So mass times the gravity constant, okay? So you do that and you get your force is 637 kilograms per meter, or kilograms meters per second squared, which is going to be a in newtons, right? Pressure then is that divided by centimeters squared, right? But I need to convert that centimeter squared to meter squared, so I have to divide that by 100 twice, okay? And when you do that, you'll simplify things and you'll get 3.19 times 10 to the 6 pascals. If I want, I can convert that pascals to atmospheres, right? but yeah, so that is the pressure that is exerted on that ice, right, from the ice skates of some 65 kilogram person. Okay. Another way we can try to understand pressure and mechanical equilibrium is kind of an old setup, an old device, people called a manometer. Okay. How this works is you have some liquid, right? And what you typically do is you have your system here and some closed container, so you expect this to be closed, and then on the other side this thing is open, okay, right? And so on the left side, typically the pressure that's exerted here is just your atmospheric pressure, right? 1 atmosphere, okay? Well, on the right side, your pressure inside the system is who knows what, whatever you potentially put in there, okay? And the differences in pressure will cause a difference in the height of that liquid, okay? Right, this liquid will have a difference in height, right, this delta H, okay, that's related to the fact that more pressure is being exerted on one side versus the other, right? That more pressure means that there's more force pushing down on one side versus the force that's pushing down on the other side, and that extra force causes the liquid to raise on one side versus the other, right? And so you can work out that that difference and that difference in height is related to essentially the extra pressure that's being added to your system by the pressure of the liquid. By this extra amount of liquid that's floating around here, okay, that extra liquid is exerting some amount of pressure, okay? And so, for example, in this system, right, always the pressure on the left side, if you cut this thing in half, the pressure on the left side has to equal the right, okay? In our case, the pressure on the left side is just the atmospheric pressure, okay? That's just what P left is. And then the pressure on the right is the pressure of our system, okay? Right? Plus the extra pressure exerted by that extra liquid on the right side here, okay? Which the extra pressure exerted by the liquid is just related to the density of the liquid times the gravitational constant times the change in height, okay? And just as a reminder, right, that rho liquid, right, that's the density of the liquid, okay? Not pressure or something like that, that's the density, okay? And finally here, in this video, we'll finish up talking about temperature, okay? Right? Temperature is a measure of average kinetic energy of some substance, okay? When we talk about temperature, we'll talk about adiabatic and diathermic type processes, right? Diathermic is when temperature doesn't change between or in the system, the surroundings and such. Adiabatic is that there's no heat exchange between the system and the surroundings, okay? And as a reminder, for temperature, we'll always use Kelvin. And the reason is because Kelvin is on an absolute zero scale, right? The lowest possible value of Kelvin is 0, okay? And so that's what we need to use that type of scale for temperature, right? Because if you use Celsius, you're going to sometimes be multiplying and dividing by 0 degrees Celsius, right? Which is going to mess up all your math and all your calculations, okay? Right, like mechanical equilibrium, temperature, right, is related to what's often called the zeroth law of thermodynamics, which is thermal equilibrium. That if you have different objects at potentially different temperatures, when you put them in contact, heat will transfer between them until they reach equal temperatures in all three systems. Okay, so sort of like that pressure, if you will. Okay, instead of this wall moving now, what we have is some energy, right, in the form of heat is being transferred from one side to the other, right? It's going to go from the high temperature side to the low temperature side until it reaches equal temperatures on both sides, right? It means it has equal amounts of energy on both sides and such, and in that case, there will be no net change in energy on either side or change in temperature. Okay. So that's it for this first video on kind of ideal gases and just talking about pressure and temperature and such. In the next video, we'll talk about the ideal gas equation and where it came from and sort of empirical derivations of it.